Okay, so like I said, we are starting our Unit 4, which is on graphing. Two different styles of graphing we're going to look at. We're going to look at the standard geometric, XY graph, and then we're going to look at some data plots at the end. So we're going to start out looking at sets of numbers. Back at the beginning of the course, when we talked about negatives, we used this number line to represent numbers. And there's a couple of different ways that we went about it. For example, if I wanted to represent the number 7 on the graph, one of the things we did when we were dealing with integers especially is we used vectors. A vector is an arrow that starts at 0 and goes to that value. So for 7, the vector would look like that. And when you're adding, subtracting with integers, those vectors were very useful. But if we're going to represent a lot of numbers, those vectors can get kind of cluttered. So an alternative, rather than drawing out the full vector, is just using an endpoint system. Since that vector would end at 7, we just put a dot at 7 to represent the 7. And that's kind of an accepted, abbreviated way of representing that number, 7. So, of course, a dot right here, that would represent -3. Well, mathematically, and in the sciences especially, physics, chemistry, and so on, more important than just the list of numbers, more interesting is generally a relationship between two numbers. Height and weight, concentration of certain substances in the blood over time, things like that. So it's very beneficial to be able to display and analyze two numbers paired together at the same time. So we might have a pair of numbers like this, 3 and 7. We put them in the parentheses just to show that those are the two that are grouped together. We need to be able to represent those two at the same time and to show that there is a connection between them. This is what we call an ordered pair. Obviously, it's a pair because it's a pair of numbers. The ordered part means that they're put in order. The position of them does have meaning. 3, 7 is definitely different than 7, 3. And to represent both of them, a man by the name of René Descartes came up with a system using that basic number line that we've used in the past. That's what we started out with, is a single number line. 1, 2, 3, 4, 5. And that was used to represent the first variable, what we often call the independent variable. When we talk about statistics a little more, that term independent is going to become a little more relevant. Or sometimes called the x variable or the x-axis, since that number line is simply an axis. Then to represent that second value, Descartes drew a second number line. This one in a vertical orientation. And he numbered it positive going up and negative going down. To represent, like our 3, 7, well, the 3 goes on the first axis, that would be right here. The 7 on the second axis right there. Well, again, we don't want two dots there. We want some way to represent both numbers at the same time. So he used the projection of the axis up into space. He put a single dot right there. And that dot, if you want to think of it as its shadow, its projection, down onto the x-axis was at 3. Over onto the y-axis was at 7. So it represents both the 3 and the 7. So if we had 8, 2, we would go to the 8 on the x-axis right there, 2 on the y-axis, and we would project them until they intersect right there. Now, most of us, we're used to working with grid paper, so we don't have to worry about the projections and stuff. We can just follow the little grid lines up until they meet. Negatives come into play. It just moves it a little bit. We might have -4, 6. So -4 is still on the x. That's right here. 6 on the y there. We project them together to right there. So that's -4, 6. Or we might have 5, -3. Again, 5 is the x, negative 3 is the y. We project them together. Right there is 5, negative 3. A little bit trickier to graph are things like 0, 4. 0 means that on the x-axis, we're at 0 right here. By the way, where the two of them cross, where both of them are 0, is what we call the origin. That's where both of the number lines, or in this case axes, originate. So x is 0, which means it's going to be along this y-axis somewhere. And y is 4, so we just move up that axis 4 units. It's right there. Now there's some vocabulary you might have thrown out in your geometry class or algebra class of quadrants. Where this here is the first quadrant because both variables are positive. From there, we go around counterclockwise, second quadrant, third quadrant, and fourth quadrant. And really the main reason we go around counterclockwise is because all sorts of mathematical and scientific applications like navigation, trigonometry, all sorts of things. Even in geometry, the orientation of the vertices of a polygon go counterclockwise. So it's just kind of accepted in math that we're going to go counterclockwise on things like that. But it is pretty obvious that this is the first quadrant because both variables are positive. And that's the quadrant that's going to get used the most in real life because in real life, most values are positive. So outside of just plotting random points, random ordered pairs like this, what do we use the graph for? Well, we can use it for representing large sets of solutions or large sets of numbers. For example, we've had equations that we've solved that look like this. 3x minus 2 equals 4. And we solved it by adding 2, so 6 equals 3x, and dividing by 3. 2 equals x. So x equals 2. But we could have another equation, a related equation that looks like this. 3x minus 2 is equal to 10. Notice the only thing that's changed here is this number over here. The rest of the equation is exactly the same. The way we solve it is going to be exactly the same. We're going to add 2. 12 equals 3x. And we're going to divide by 3. 4 equals x. So the steps to solving it were exactly the same. The only difference, again, the value of x was different. What these are called, they're called a family of equations. And we can't possibly create all of them and solve all of them. So what we do is we represent it with a generic variable here as well. So instead of 4 equals 3x minus 2 or 10 equals 3x minus 2, we say y equals 3x minus 2. This now represents an infinite many, all of the possible equations of that form, 3x minus 2, and all the possible numbers that could possibly go over here in place of y. To represent that, there's going to be an infinite number of possible solutions, so we can't just list them out. We can start listing them out, but we need some way to fill in the gaps in between. For example, let's start listing some of them out. I'm going to pick values for x and figure out what y has to be from that. Now, I'm going to pick out different values. I might do like a negative 2 for x, a 0, and maybe a positive 2. Well, if x is negative 2, y is 3 times x minus 2. So 3 times negative 2 minus 2. Well, 3 times negative 2 is negative 6. Negative 6 minus 2 is a negative 8. So we get negative 2, negative 8 is an ordered pair. Well, that can go on our graph. Negative 2, 1, 2, 3, 4, 5, 6, 7, 8. Negative 8 is right there. There's a point on our graph. If x is 0, y is 3 times 0 minus 2. 3 times 0 is 0, minus 2 is negative 2. Well, 0, negative 2. Again, an ordered pair is a point on our graph. 0, negative 2 is right there. Let's try when x is 2. Well, if x is 2, y is 3 times 2 minus 2. 3 times 2 is 6. Minus 2 is 4. 2, 4. Is that ordered pair? So we got 2, 1, 2, 3, 4. There's a point right there. Now at this point we can see that these form a straight line. They're lined up. I would probably pick out one more point just to be sure. So maybe I'm going to pick out, let's just use x equals 3. This is 3 times 3 minus 2. 3 times 3 is 9, minus 2 is 7, giving us the ordered pair 3, 7. So let's try that out. Here's 3, this was 4, 5, 6, 7. And it does appear to be staying in a straight line. Now what does this line represent here? Well, this line that we just drew through the points represents all of the solutions to the equation 3x minus 2, or y equals 3x minus 2. I can pick any point on that line. Let's say right here. I pick this point, I can trace it down to get an x value. Let's say that's 2.5. I can trace it over to get a y value. If I drew this correctly, that should be at 5.5. If I plug those numbers in here, if I put 2.5 in for x and 5.5 in for y, I should get a true value, a true statement. That was the same value on each side of the equal sign. Or I might pick out a point down here where x is -1, y ends up being -5 if I draw that correctly. Or I might find a value. Maybe I want to know what value of x is going to give me a y value of 0. Well, I can trace it over and up to x. Y is 0 is right here. I trace that up, and I end up getting, what is it, 2/3 is where that ends up being at. So x is 2/3 makes y 0. So any value, any possible solution to this equation is going to be a coordinate on that line. And any coordinate that's on that line is going to be a solution to the equation. Well, not all of our equations form straight lines. We can have something like this. Y equals x squared plus 2x minus 15. I'm going to do the same strategy. I'm going to make a table. I'm going to pick values for x. And I'm going to figure out what y has to be. Make a graph over here. And I'm going to pick -2 for x again. So y then would be -2 squared plus 2 times -2 minus 15. Well, -2 squared is +4. 2 times -2 is a -4 minus 15. Well, 4 plus -4 is 0, minus 15 is a -15. That gives us a coordinate or ordered pair of -2, -15. So let's mark it out. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right there is a point. Let's try 0. If x is 0, y is going to be 0 squared plus 2 times 0 minus 15. Well, 0 squared is 0. 2 times 0 is 0. Well, 0 plus 0 is 0. Minus 15 is -15 again. So we get a point at 0, -15. That would be right there. Let's try a different one. Let's try +2. So that's going to be 2 squared plus 2 times 2 minus 15. 2 squared is 4 plus 2 times 2 is also 4 minus 15. Well, 4 plus 4 is 8 minus 15 is a -7. So we're at +2, -7 is right there. Well, it is pretty obvious right now that this will not be a line because those 3 points are nowhere near lying on a line. But also at this point, we don't really know what this is going to look like, so we have to keep going. But we don't have to just blindly keep picking points for x to see what we get for y. We can look at our graph here and see where do we need more points. For example, over in here, I need some point to see what happens over there. And I probably do need at least one more point over here to see what's going on. So let's pick some points. Let me pick the point x equals -3. Let's see what happens with that. So I have -3 squared plus 2 times -3 minus 15. -3 squared is 9. 2 times -3 is -6 minus 15. Well, 9 plus -6 is 3. Minus 15 is a -12. Giving me the point -3, -12. So -3 would be there, -12 right about there. Probably still not all I need. I'd probably still need to go one more, maybe to -4 or -5 or something like that. Let's go a little further. Let's do -5. This is -5 squared plus 2 times -5 minus 15. So -5 squared is 25. 2 times -5 is a -10 minus 15. You add that all up, you're going to get 0. So -5, 0 is a point on this. So this -5, 0 is right there. And now I'm not going to keep picking points and plugging them in here for you because I don't want to keep beating a dead horse here, but we would probably pick like -1 to see what we get here. We get a point right here at -1, -16. We might try +1, which would give us +1, 12. Or +3 would give us 3, 0. -4 would give us -4, -7. You get enough points there, we can see this graph is going to look like that. Many of you, if you've done much graphing, can see an equation like this and see that there's an x squared in it and know that it's going to make this kind of U shape that we just graphed called a parabola. Now you have to be careful, just having an x squared in it isn't enough. It has to be what we call a quadratic form, where x squared is the highest power and there's no other funny things in it like square roots or anything like that. One of the things we will go over at some point is shortcuts for graphing a parabola, quadratic equation, or lines like this. In fact, that's what we're going to start on right now, is some shortcuts for graphing lines. Well, first of all, when we graph equations, we need to know what shape it's going to make. The line is probably one of the more useful graphs that we're going to run into. Linear equations are very common. Between the linear and the quadratic or the parabolas, parabolic equations, that describes most of what we do in engineering and other sciences, and even in economics. Along with maybe a slight exponential curve would be pretty much all you would need. So let's start out talking about linear equations. And the first thing we need to be able to do is we need to be able to look at an equation and identify, is it going to be linear? Is it going to form a straight line? And normally what I would have you do is I have a worksheet that I would pass out to you and have you guys fill that in. Because most of you have had experience graphing before, I'm not going to do that. What I'm going to do is I'm going to pull up the worksheet and we're just going to sketch in the graphs right now because I'm going to trust that you guys can handle filling in the charts and graphing the equations. So there's my graphing worksheet. So I'll make this a little bit larger so we can see each graph a little better. And this is one you could fill in the tables and graph these. And normally, like I said, if this were a group of returning students that hadn't had algebra and geometry for quite a while, or a group of students that I knew had never had it, I would have you guys go ahead and fill in these tables and plot the points and make the graphs. But since I know most of you have had this in the last couple of years, We're just going to go ahead and fill this in quick. So if I were to complete the table here and graph y equals 3x minus 2, I'm going to get something that looks like that. Obviously, I can look at that and see that it's going to form a line. Number 2 here, same way. I know that's going to be a line. That one's going to end up being graphed like this. If any of you off the recording want to look at this worksheet and jot them down and plot the points and graph them just to make sure you can, please feel welcome to. This one here now is not going to form a line. What's different about this one from the first 2 equations? Well, the big first thing that sticks out to us, and we talked about it before, is the x squared. Having that x squared means this will not form a line. It has a power on the x. Having a power on the y would do the same thing, but normally when we're talking about functions and graphing, we don't do anything to the y. The y ends up being by itself. Or we solve the equation so that the y is by itself before we do any sort of graphing. So having a power on the x means this will not be a line. What it will end up being, however, is a parabola, looking something like that. Oops, if I can draw it well. There you go. Over here, number 4, this one's also not going to be a line. The thing that sticks out there as being different is that square root symbol. Well, believe it or not, that square root symbol is the same as a power, so that falls in the same category as over here. There's a power on the x. Technically, the square root of x plus 6 is really x plus 6 to the power of 1/2. A square root and a power of 1/2 are the same thing. This one then is going to get graphed. It's going to look like that. This one you'll notice, all of the graphs I've done so far, there have been arrows on both ends. This one only has an arrow on this end, because this end cannot keep going. It can't go over here because of the way this is set up. If x were to be -7 here, -7 plus 6 is a -1. The square root of -1, if we tried to put that in our calculator, is going to give us an error. If you've had any Algebra 2 or pre-calc, you might know that they've defined imaginary or complex algebra where they've defined the square root of -1. But for our purposes, we're going to say that the square root of a negative cannot be done at this point. And we don't have a complex graph here, so there's no way we could graph it on this graph anyway. So this line has to stop here and cannot continue on to the left at all. So that's why there's no arrow on the end of it. Number 5, from what you guys know so far, is there anything here that would keep that from being a line? Well, no, there's no powers on the x or no roots on the x, so this should form a line, and it does. Just like that. Number 6. Well, our first instinct is the powers, but there's not a power on the x. In this case, the x is a power. It is the exponent in that case. This, again, will not be a line. This graph is going to look something like this. There are arrows on both ends. This one shoots off up steeper and steeper. This one here gets closer and closer to 0 without ever touching it. Since it gets closer and closer to 0 without touching it, it gets closer and closer to that x-axis without ever touching it. That brings up a term we often call an asymptote. An asymptote just means it's a line, the graph approaches it but never touches it or never crosses it. It's a limit to the graph. Coming down here. Number 7. Is there anything that would keep that one from being a line? Well, there is. It's not a 2, it's not squared, but it's a power of 3 on our x. There's a power on the x. So that keeps it from being a line. This one's going to look something like this. A cubic curve. Number 8 over here. If we look at what we've done so far, of having a power or root on the x, or having x be a power, this one doesn't appear to have either of those. But it actually really does. Technically, this, having x on the bottom of a fraction or dividing by x, is x to the power of -1. Remember we talked about that with our scientific notation and powers of 10, negative powers or reciprocals or whatever. So if x is as a negative power, power of -1, or another way of wording is if we divide by x, it's not going to be a line. So for this graph, this one's actually kind of tricky. I'll put the dots in. It's hard to just sketch it right in. We had a line, a curve that looks something like this. But you'll notice as x equals 0, if I try to put x equals 0 in there, if you punch that in your calculator, 8 divided by 0 is a problem. We cannot divide by 0. This line can never go through x equals 0, can never cross that y-axis. That is an asymptote again. Graph can never go through that line. But in this case, there is a graph on the other side. It does continue. It shoots off down to -infinity here, and it comes back in from +infinity up here, giving us a very similar curve up here, like that. I mentioned that idea of dividing by 0. We've discussed that before, how dangerous it is if you can divide by 0. I'll show you an example here in just a second of why dividing by 0 is such a horrible thing. Here, this one, of course, there's the x squared. So that's not going to be a line. It's going to be a very, very narrow parabola, something like that. Oop, narrower than that. There you go. Something like that. And finally, number 10, yeah. We don't have any powers on the x or roots on the x. X is not a power. We're not dividing by x. That one is going to be a line. It's going to give us something like this. So we can very quickly look at these equations and identify whether they're going to form a straight line or not. So will it form a line? The list of things. No power or root on the x. No dividing by x. And x can't be a power. So given several equations, looking at these, we can very quickly identify which ones will make lines. Yes or no? First one, will this be a line? Not everybody at once. Well, we see that power of 2 there, which makes us a little leery, but the power of 2 is on a number. 3 squared is 9. That will be a line. How about this one? No powers on the variables, no roots on the variables, not dividing by x. None of the variables are powers. That one will be a line. This one, we're dividing here, but we're not dividing by x. So yes, that'll be a line. This one, no, there's an x squared. That one's not a line. And here, even though the x appears twice, it's a 3x and a 7x. That just combines to be a 10x, which is just fine. So we can identify which equations are going to form lines. some things for you guys to work on for homework before we lose time. Then I'm going to show you, I said I'd show you something about dividing by 0 and why that's bad. On page 215, I'd like you to look at 1 through 3. I'd like you to look at all 3 of those. And on page 215, I think it's 205 is actually the page I want there. Excuse me, page 213 through 217. On 1 through 15, the odds. Just some basics of graphing. Now, in our last 6 or 7 minutes here, let me show you quick a little example of why dividing by 0 is a bad thing. It's kind of along the lines of your geometric proof. Let's do x equals 1. I can modify this equation. I can add, subtract, multiply, or divide both sides by the same thing. So what I'm going to do is this. I'm going to multiply both sides here by x. So x times x is x squared. 1 times x is x. So far I've done nothing wrong. Now I'm going to subtract 1 from both sides. I can do that just fine. X squared minus 1 will be x squared minus 1. X minus 1 will be x minus 1. If you've done any factoring, you know that x squared minus 1 is x plus 1 times x minus 1. And we got just x minus 1 over here. Division, we can divide by x minus 1. Well, dividing by itself, anything divided by itself is just 1. Over here, if I divide by x minus 1, this cancels out and I have x plus 1. I can subtract 1 from both sides, giving me x equals 0. All this seems really innocent until we go back to the very beginning and realize we started out as x equals 1. So I started out with x equals 1 and I ended with x equals 0. That can't be. The only way that is possible is if 1 equals 0. And hopefully most of us at this point in life accept that that is not true. So the question I pose for you, you email it to me and I'll give you a bonus point for the day. If you can explain to me what I did that was wrong in that little exercise there. Remember, my email address is todd.hoff@witc.edu. Send me an email pointing out to me what I did wrong there that created that problem. Okay, with that, I will let you guys out of here.